Okay, so let's talk how they could have spun this problem differently. So on the first one, they said, okay, hey, here's the grams of methane gas and containing 2.58 moles of chlorine. So if you do the conversion of the grams of methane into moles of the dichloromethane, you get 1.56 or you get 1.29. So which one can you make? The bigger amount or the smaller amount? Smaller. So you can only produce 1.29 moles of this dichloromethane. Never the bigger amount. Like if I can make 5 sandwiches based upon bread and I can make 6 sandwiches based upon cheese, I can only make 5 sandwiches because the bread's going to run out first. Now, what they could have done, which they didn't, they'd been a jerk if they had, but I've seen it done. They could have said, what's the total number of moles left over in the container? So all the chlorine would have gotten consumed. But you would have some CH4 left over because not all of that got used up. So if they did that, okay, you would have to start with the 1.29 moles of this dichloromethane. You'd have to start with that, moles of your CH2Cl2. And then you'd have to work backwards and say, okay, how much of that CH4 would get consumed in the production of this? And then whatever is left over, that would be added to the total number of moles of gas in the vessel. Now, in terms of rates, okay? So keep this in mind, like on Thursday with this test. So if you look at this equation, so you're and everything here is gaseous phases. So you've got methane as a gas, chlorine as a gas, you're producing the dichloro as a gas, and the hydrochloric acid as a gas. So remember that you can when you're talking about rates, you can either talk about pressure changes or you can talk about mole changes. So as this stuff gets consumed, if that's all that was happening is if you were consuming this, the pressure would drop because you would be decreasing the number of moles inside the vessel. But you're also producing nothing but gaseous products. Okay? So remember that you can look at this in terms of pressure, you can look at it in terms of mole. So if it said, hey, this thing is consuming so many torr per minute of your CH4, what would be the increase in production of your dichloromethane? So, because these are 1-to-1 ratios, so if you were consuming like 500 torr per minute of your CH4, you would be producing 500 torrs of this dichloro because that's in a 1-to-1 ratio. But if you do the math on your HCl, if you did that and you're starting with 500 torr, okay, well there's a 1, there's a 1, there's a 2, so you would actually be producing 1,000 torr of pressure over here in terms of your HCl. So just keep in mind, on this test on Thursday, you can work this in terms of moles, you can work it also in terms of pressure, in terms of how that's going to play out. Just keep that in mind. Okay, so your answer to part 2 then is that 1.29 because you can only produce the smallest amount. Now, when you get to B, so when you get to B, you want to pay attention to the units as calculate the amount of energy in joules, okay? Not kilojoules, in joules needed to break a single chlorine-chlorine bond. So you got 242, you just want to shortcut it and go 42,000 joules per 1 mole of chlorine. Now, what units do you want at the end? You want joules basically per bond, right? So, right? Well, this is chlorine, so if I put 1 mole of chlorine up there, how many particles or molecules are there in 1 mole? 6.02 times 10 to the 23rd molecule. Now, look what happens. The moles cancel out. You get joules per molecule. And that's what you want. So that answer on B is a really, really small number. It's like 4.02 times 10 to the negative 19 joules per bond. Okay? Cool. Now, once you get that, then you want to go to C. Oh, now we're going to find out the wavelength that's associated with this. Now, if you get a really, really big answer there, that's going to translate into a really, 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 really weird, wonky number down below when you calculate that wavelength. Because wavelength of light is usually like a really small number. Okay? So if you solve for that, you get lambda equals hc over E, and you plug in all of that, you get 4.95 times 10 to the minus 7 meters. Okay? So what we're saying is that imagine, if you will, that here's the two chlorine atoms, okay? And they're held together by a bond. There has to be a bond, or otherwise they wouldn't exist as chlorine gas. Okay, so there's some bond that holds them together. So basically what we're saying is that what photon of energy we can shoot in between that would break these things apart. That's what you're trying to find. Like, how much energy does the bullet have to split these apart? So, now, but the beauty of this is, technically it says, what's the longest wavelength of light in meters? Now, here's the question. If you look at this relationship of E equaling hc over lambda, if you made that wavelength longer, would that still have enough energy? Why? Your answer is right.
Because if you increase the denominator, that will likely be less.
Yeah. Since you're dividing by wavelength, okay, if you made this any longer, you wouldn't have enough energy. Now, you could shine light on it, but nothing's going to happen. So that's why this is the longest wavelength that you could have. If you want to be on the safe side, you make that shorter because that would have more energy. Okay. Now, let's talk about that next question. So this is what we talked about, this whole idea of like rate determining stuff. So this has a whole bunch of mechanisms. This is like 5 steps, okay? Now, what's the rule? What determines the rate of the reaction? The fast steps or the slow steps? Slow steps. You cannot go faster than the slowest step. It's just like, okay, hey, you have a bunch of people that are running, and you're trying to get away from whatever, mermaid, the bear, or whatever, then everybody has to make it. That's the rule. Well, you can't run faster than the slowest person. Just saying. Stay with the story. Now, there's another important part of this. Up there at the top where it says step 1, notice that has the fast equilibrium. So you have Cl2, double arrows, Cl. Okay? What that means is that, conveniently isophoresis here, so imagine, if you remember when we did that demo with the containers of water, okay? And that initially shifted really, really quickly because Isaac had that big beaker and I had the tiny little beaker, but eventually it leveled off. We didn't say the reaction stopped, the reaction just leveled off, okay? The water level stayed the same. So what we're saying is that because this can reach an equilibrium, that formation of CO2 and 2Cl can reach an equilibrium where the forward and reverse rates are the same. That's going to be an important part of this. So, in the mechanism, CH3Cl, is it a catalyst or is it an intermediate? What do you get? Why? It's made and consumed. So, all catalysts do, this is a bigger picture in terms of that test on Thursday as well. If you remember those activation energy curves, like here's the amount of energy that you need, and here's how the reaction proceeds, and that's your activation energy, okay? All catalysts do, there's a couple of things to remember about catalysts. All they do is that they lower the activation energy. It does not change the delta E. It just lowers the activation energy. So it's just like you're out on the second grade playground and you lower the bar. More kids can jump over the bar, okay? That's kind of like what the catalyst does. But catalysts don't show up. Okay, the only time you typically see a catalyst written, so it might be like something like 2H2O turning into H2 and O2. And let's say you use platinum to catalyze this reaction. Typically, where the catalyst occurs is that it shows up on the arrow up above, and that just says, hey, this is the catalyst. Okay, the other thing about intermediates is that when you add the reactions together, intermediates don't show up in the overall reaction. We're not saying they're not there. We're not saying they're not important. They just don't show up. They're the wizard behind the curtain pulling the levers. Okay. So, E. One of these is really easy, and the other one's tricky. Okay? So, identify the order of the reaction with respect to each of the following according to the mechanism in each case. CH4. Now, the whole key to this is that you have CH4 plus Cl turning into CH3 plus HCl. And that's identified as a slow step. Okay? So there's a couple of things to consider. First off, there's no coefficients in front of the CH4. Okay? There's nothing there. It's just boom, CH4. If there was a 2, then you might think, well, maybe that's second order. Okay? Because remember, if there's like a 2, you cube it. If there's a 3, if there's a 2, you square it. If there's a 3, you cube it. Okay? But since there's nothing there, that would kind of lend it to the idea that, oh, okay, right, hey, maybe this is just first order. Now, the other reason that that supports it, number one, it's in the slow step. And in the overall reaction, if you look at that CH4 plus 2Cl2, notice that with that one, there's no coefficient up there. So there's two reasons you would say it's first order with respect to the CH4. In the slow step, the coefficient is 1. And in the overall reaction, the coefficient is 1. Okay, so that would be your justification for saying that it's first order with respect to the CH4. Now, the second one, they were a jerk. And people, you read the forum. Yes, there's a forum of AP chemistry teachers, and they talk about tests. So people were saying they were a jerk on part 2, and I'll tell you what. So if you look on part 2, on that equilibrium step, where you have Cl2 reaching into an equilibrium of 2Cl, okay? So what we're saying is that because this can reach an equilibrium, so K of the forward reaction times some Cl2, and remember that K is just some rate constant, okay? And that would equal some other K constant in the reverse times Cl2 squared, okay? Now, this is where this gets a little bit sketchy in terms of why people were upset, mainly because of the fact that you generally don't do this. So if you were to look at this in terms of solving for the Cl, okay? And here's why you would want to express this in terms of Cl. The reason that you want to express this in terms of the Cl2 is because that's what's in the reaction, okay? The Cl, in the broader scheme of things, if you look at that overall reaction, okay, Cl is also an intermediate. So you can't have Cl showing up as part of the rate law because it's also an intermediate. So the Cl's there, but it can't have it. So what you need to do, and this is where this is kind of a multi-step process. So if you solve this thing for some value of K, and you wanted to isolate the Cl because the Cl can't be there because it's an intermediate. Oh, so I'm going to divide by K of the reverse, okay? So this is just going to be a different value of K. Anytime you divide K, you just get a different value of K. So you get K, and then times the concentration of the chlorine equals the concentration of Cl squared. Okay? Now, but you can't have Cl in the reaction. So to get Cl by itself, what are you going to do? Square root of it. So you get K to the 1/2 Cl2 to the 1/2. There's your answer. So what you would do for the overall reaction is that you would have R equals some K times the concentration of your CH4 times the concentration of your Cl2 to the 1/2. And the AP teachers were upset because it's like, look, this is such a rare occurrence that you have something to the 1/2. Typically, it's to the second order. It's to the third order. So, College Board got skewered for doing it this way. But if you understand the process, it's like, oh, okay, it's just to the 1/2. But here's the bigger idea, is that I can't have it in terms of Cl because of the fact that that's an intermediate. But I can put it in terms of the chlorine molecules because that's in my overall reaction. So that was a bit extreme, but it's still the same process.
So it's half order?
Okay, yeah, it's just a half order. Like I said, that doesn't happen very often, but it does. Okay, so real quick, try that 2015 on voltaic cells.